We know that the Fermi-Dirac distribution is given by 1 over e to the difference between the state energy and the Fermi energy over kT plus 1. And from the graph we can see that the energy of the state equals the Fermi energy plus 1/2 of the gap energy. So that means that the energy difference between the state energy and the Fermi energy is half of the gap distance. And if we divide both sides by kT, we can find the term that is needed for the Fermi-Dirac equation. And we know that if there's a gap difference for part A, if there's a gap difference of 0.2 electron volts, then this energy difference is going to be half of that, which means that E minus E sub F is going to be 0.1 electron volt, which means if we take the Fermi-Dirac distribution, we would get 1 over E raised to the 0.100 electron volts divided by K, which we can rewrite as 8.617 times 10 to the minus 5th electron volt per Kelvin times the temperature in kelvins given, which is 300 kelvins plus 1, and that will give us a probability of 0.0205. If we repeat the same steps but for t equals 310, then we get that E gap over 2 kT would equal 3.74, which means that the Fermi energy then, or the probability, would be 1 over e to the 3.74 plus 1, which will give us a probability of 0.0231, and this is about 13% increase. This is not part B, by the way. This is just continuation for part A. Now for part B, the energy gap now is 0.1 electron volt. So that means it's going to give us Eg over 2 kT of 19.3 for T equals 300, and for T equals 310 it would give us 18.7, and plugging these into the Fermi Dirac probability, we get 1 over e to the 19.3 plus 1, which will give us a probability of 1.0 times 10 to the negative, 4.0 times 10 to the negative 9. And if we put the temperature at 310, we get 1 over e to the 18.7 plus 1, which is 7.4 times 10 to the negative 9. And for part C, the energy gap is now 5.0 electron volts at T equals 300 Ks. We get an Eg over 2K T value of 96.7, which means that we have a Fermi Dirac probability of 1.0 times 10 to the negative 42, and for T equals 310 Kelvin, we get an exponent Eg over 2 kT of 93.6, which gives us a Fermi probability of 2.3 times 10 to the negative 41. And you see, as the energy gap increases, the probability decreases for finding an electron in those energy gaps.